Good evening. Welcome to our third July lecture in physics for 2016. My name is David Jamieson. I'm the organiser of the July lectures in physics since 1990, but the lecture program has been running every year since 1968. Can I just ask for a show of hands if there's anyone here who was present at the first July lecture in 1968? Oh, thank you, sir. Welcome to the 2016. Needless to say, I was not. Ladies and gentlemen, we are celebrating the 100th anniversary of Einstein's most magnificent theory, the general theory of relativity, with our 5 lectures this year. Tonight, I can think of no better person to participate in this celebration. Professor Matthew Bales, well known to me, a friend and colleague for many years. He is one of Australia's, indeed the world's, leading astronomers. He served for 5 years as a Queen Elizabeth II postdoctoral fellow here at the University of Melbourne, one of the most distinguished fellowships it's possible to hold as an early career researcher. When that concluded, he was headhunted, I would say, to head up the new Astrophysics initiative at the Swinburne University of Technology. He has built that program at Swinburne to a major program of international significance that hosts a large number of distinguished fellow astronomers and has a very long track record of accomplishments for original breakthroughs in observational and theoretical astronomy. A unique feature of his centre is successive generations of supercomputer facilities necessary for performing advanced astronomical simulations, as well as rendering some very sophisticated animations, I must say. He has discovered a large number of pulsars, which he will talk about tonight, mostly using the Parkes, or many of which use the Parkes radio telescope. Some of you may be familiar with that from the classic Australian movie, The Dish. Yes, he was one of those guys who uses the dish. So, Matthew, please tell us about pulsars tonight.
Thanks very much for that nice introduction, David. I'm currently a professor at Swinburne, and I'm part of the Centre for All-Sky Astrophysics, which is an ARC Centre of Excellence. And sitting on the Federal Minister's desk is the decision about whether the ARC Centre of Excellence for gravitational wave discovery will be funded or not. So it's a little bit cheeky to have this up here, so please don't leak this to the Minister. It would seem a bit presumptuous. But there are a bunch of us around Australia who are very excited by gravitational waves at the moment. And before they were even discovered, we put in an application for this thing called OzGrav, which is to develop a centre of astrophysics, a centre of excellence around gravitational wave discovery, and it includes the University of Melbourne. So it's very nice to be back here on the eve of what we hope will be an announcement about this new centre. But I'm going to tell you a bit about what I've done in my old centre, which is the Centre for All-Sky Astrophysics. So gravitational waves were discovered spectacularly last year, and I'm sure you've already heard a bit about this. And for years we've been looking at curves that look a little bit like this, which was going to signify the death spiral of two relativistic objects. And it's actually incredible to see that it's real. You can actually detect these things. And it was enabled mainly because of this man, Albert Einstein, who over 100 years ago now predicted the existence of gravitational waves. And I think it must be the longest time in history since a theoretical prediction and an experimental discovery. And at the time that he predicted gravity waves, he calculated what their amplitude would be and how big something or how heavy something would have to be, and in order to generate a wave that we'd have a snowball's chance in hell of detecting. And he thought they were effectively a complete fantasy. And in fact, he even drafted a paper in which he submitted it saying he didn't actually think gravity waves existed after all. And luckily, the editor or the referee rejected the paper. And so he got to, well, he didn't really get to claim the credit because he's been dead for many years now. But amazingly, last year, 2 black holes were seen to coalesce by this amazing piece of instrumentation, the Laser Interferometric Gravity Wave Observatory, LIGO, and there's actually 2 of these things on either side of the continental US, and they both vibrated in a way that was predicted from Einstein's formula if 2 black holes coalesced. And in fact, this is our kind of logo, and hopefully it's going to lead to OSGRAV. And we're exceptionally lucky that we put in our application about 3 months before they were discovered. So it was a very nice thing for them to occur. Hang on, let me just address a technological challenge here. It was very timely that they occurred while our application was being judged. So we'll see what happens there. So the amazing thing about these gravitational waves is that they really don't have much impact on you when they pass through you. The 2 detector traces are here with these lines to guide your eye, which is a trick that physicists use. But the 2 detectors on either side of the continental US look a little bit like this. They've got these 4-kilometer long arms, and laser beams are shot down and split 2 ways. And when the gravitational wave goes through, it causes the mirror to move, and this changes the path length here. And what this interferometer is very good at is detecting the change in these path lengths. And incredibly, there were 2 black holes in a galaxy about 1 billion years away coalescing, and this whole time here, from here to here, is just 1/10 of a second. So in about 2/10 of a second, this instrument was capable of watching space-time being compressed up to a few hundred times a second. And the amplitude of this wave here was only 1/10,000th the size of a proton. and yet this was able to be detected. And I think this is one of the most outstanding achievements in experimental physics. And it got the romantic name GW 150914. And so here's where the 2 detectors were, and one of the gravitational wave passed through one detector. I think it was about 7 milliseconds before it hit the other, because gravitational waves travel at the speed of light. And so that enabled, I guess they're now astronomers. They used to be called physicists, but now they're doing astronomy, to determine that the source came from a very large error box on the sky. And for the bargain price of only $900 million, they managed to detect this event. And Australia was not just watching from the other side of the world. My colleagues at ANU provided the lock acquisition system. In Adelaide, they provided the Hartmann cameras. At the University of Western Australia, David Blair's group worked on sort of suspension devices that helped control the mirror and so it wouldn't go crazy when the laser beam hit it. At Monash University, Eric Thrane worked on the blind injection system, and there's data or people working on data from this telescope at various institutions. And of course, our friends at CSIRO, before this part of CSIRO was shut down, worked on the mirror coatings. So it's very exciting for people to be involved in such a discovery. It was on the front page of the New York Times, and the paper announcing it was so popular that it was being downloaded 10,000 times a minute from the server until it crashed because it couldn't cope with the demand. And I really like this hashtag, Einstein was right. I don't tweet a lot, but it was very nice. And there's been money flowing Unfortunately, there's 1,006 people, I think, on the paper, so they all got a share of this prize. But it's still better than nothing. So what is this that we've discovered? Well, it's a new window of exceptional clarity. If you look at a normal galaxy that's full of stars, you notice there's all this dust and so on, and that blocks the starlight. Gravity waves have the nice property that they just travel straight through all this dust and are very unimpeded. And so this leads to a number of questions. How right was Einstein? He's looking pretty good at the moment. What and where are the sources of the gravitational waves? And if you really want to study extreme physics, there's no better place than to use two black holes orbiting each other at about half the speed of light and tearing each other apart. Well, this is also a way of potentially looking right back to the dawn of time shortly after the Big Bang, where we might be able to see some sort of background of gravitational waves. So this was my sales pitch to the Centre of Excellence committee that's deciding whether we should do this. But I'm interested in this because I'm a pulsar astronomer, and the reason that LIGO was built in the first place was because we knew about neutron stars and pulsars, and I'm going to teach you a little bit about them. So we live on planet Earth around the Sun, and I've actually blown the size of the Sun up there so you can see it. But turn my lights down a bit.
Yeah, I think so. Get the maximum impact. Yeah.
Thank you, David. All right, so Australia just went by. I'm going to put the brakes on here and zoom out a little bit. We're very fortunate in Australia in that if I put on the spin axis of the Earth, the North Pole actually points away from where most of the stars are in the galaxy. So if you want to study stars that are in our galaxy, you're better off being on the underside of the Earth than you are on the top. And for that reason, and if you look carefully as we zoom in here, the number of technologically advanced, stable democracies that can actually see the galactic center is few. We've got a few military dictatorships and so on. We've got Australia, we've got New Zealand, Madagascar, South Africa, and that's about it. So I'm very fortunate to be an Australian because it means I get sort of an uncompetitive view of many of the stars in our galaxy. Of course, the Earth isn't the center of the universe, and I can actually speed up time here. And of course, for a long time we thought the Earth was the center of the universe, and that the moon went around the Earth and that the sun did too, and the various planets. But this actually gave rise to a very unusual frame of reference, because when we looked at planets like Jupiter here, again, I've blown Jupiter up to be a little bit bigger than it normally would be if it was to scale. It would just be a pixel, which wouldn't be very interesting. But you can see that Jupiter, during the course of a year, looks as though it's traveling in one direction, then it kind of stops and moves backwards. And then 6 months later, it actually accelerates again and moves around. And the ancient Greek astronomers noticed that not all of the stars in the night sky were fixed. There were these things that wandered. They called them the planets, but they had a hard time understanding why they went in such a strange path. And if I do this even faster, you'll see that over the course of the year, Jupiter goes backwards and then goes forwards again. And so this is a very odd circumstance, and it's because although we're on the Earth, the reference frame that's appropriate is actually the Sun and not the Earth. And so this gave the ancient astronomers a bit of a headache, and they actually invented something called an epicycle to explain it. And these days we know that the real center of the solar system is actually the sun. And if we orient this in the right direction, and now turn on the planets, they all travel around in these nice elliptical paths. And Kepler showed us these paths. Of course, there's planets further out. And if you've always wondered why Pluto is no longer a planet, if we look at this system edge on, you'll see that almost all of the planets are in this nice disk, but Pluto's in this funny orbit, and it's not very heavy, so it's been demoted. Right, we might... It's a bit loud. Can I mute? Here we go. Maybe that'll do it. All right, I'm not sure if I'm muted as well. To give you an idea of scales, we actually made a film at Swinburne, and we're going to start here on the Earth, and I'm just going to show you how big the stars are. So there's our little astronauts. They're of order 2 meters high, and we're going to zoom out and get a feel for the size of the moon, and then the size of other things in comparison to the moon. So we've lost our little lunar module here. These craters are quite large. The moon is about 400,000 kilometers from the Earth, and the Earth is 40,000 kilometers around the equator. In fact, the original meter was defined that there should be 10 million meters from the North Pole to the equator. So it's very hard for us to imagine the size of the stars, and so a nice way to do that is to put them in direct comparison to each other. So the moon is coincidentally just big enough to block the sun, so we can get a total lunar eclipse. And if you look at the edge of the moon during an eclipse, you can see these solar flares erupting from the sun. But the moon is actually a very tiny object. The smallest planet, Mercury, is just a little bit bigger than the moon, and it gets called a planet, which I think is a bit unfair. There's Mars, Venus, and then Earth is next. So it's 40,000 kilometers around the Earth, but you can see these rocky planets are very small compared to planets like Neptune, Uranus, and the beautiful Saturn with its ring-like system. Saturn's only a smidgen smaller than Jupiter. But compared to the Sun, the planets are very small. So in a minute, we're going to see what Jupiter's like in comparison to our Sun. The Sun's actually 700,000 kilometers in radius. And so you can fit about 1 million Earths inside the Sun. It's an amazing waste of energy, really. But it's quite a nice star to live around. And yet the Sun is not the biggest star in our galaxy. We call the Sun one solar mass, which is a nice unit. It's about 300,000 times heavier than the Earth, and about 1 million times the volume. And in the core of it, it's burning hydrogen, and that's causing it to shine. Alpha Centauri is the nearest star, slightly bigger. And then if a star gets hot enough, it actually turns blue. So Sirius is the brightest star in the night sky. But there are plenty of other stars that are further away and brighter than Sirius, but they're so far away they don't appear as bright. This is called a blue supergiant, and these things can be 1 million times brighter than our Sun. And then finally, when a star ends its life, the outer layers peel off, and we get red giants such as Betelgeuse. And our star's way down here somewhere. And then this star in Canis Majora has recently been discovered and is larger still. So you can see that we're actually pretty puny by some standards. And then the number of these stars that are in a galaxy is around about 10 to the 11, or 100 billion. So we live in a galaxy full of these stars. Most of them are pretty boring, but it appears that almost all of them have planets, and that the very largest of these stars do something interesting when they die. So this is a kind of animator's impression of the Milky Way, sort of a central bulge, and then these outer spiral arms. And it's quite a disk-like system. But not all of the galaxies in the universe look like this. Ones that spin, rotate very fast, tend to be these large disks. If you're not spinning very rapidly, you don't form a nice disk, and you end up a more egg-shaped system. So there's about 100 billion of these galaxies in the universe, and so we're really quite insignificant. But luckily, we can build telescopes that teach us about the number of these galaxies and our hope of detecting exotic things in them, like black holes that want to destroy each other. So we'll just let this run. The galaxies form these nice filamentary groups called clusters and superclusters, and we believe the universe is about 13.6 billion years old.
Size is one of the most elusive concepts of all. Wow, the Earth looks real big from here.
Okay, so this is a real picture of a galaxy, and it's one we think looks a little bit like where we live in. It has this central bulge in the middle, a bar, and these beautiful spiral arms. And we think we live in a spiral arm, although the Milky Way Galaxy has more than just 2 spiral arms. It's thought to have quite a few. Here's another galaxy, possibly looks a bit more like the Milky Way, M81, from a catalogue produced over 100 years ago. And you can see that in the galaxy, in the arms, there's these little blue areas. That's where stars are being born today. The oldest stars are red, and the dust makes the galaxy look even redder. If we zoom in a bit, we can see this dust. Originally, after the Big Bang, there was no dust, but dust is produced from dead stars. It's the product of chemical evolution that occurs. And some of these have these nice shapes. This is a Sombrero galaxy, again showing the dust lanes. And this is one of those galaxies I was talking about, which doesn't have a disk. It doesn't have a net rotation, so it doesn't collapse to form a disk. But it's surrounded by all of these other galaxies. And each one of these probably has 100 billion stars or so. So the number of stars in the universe is extremely vast. And if we just come here, this is one that's very edge-on, and that's the view we get of our own galaxy, which is here. So if we look out at our own galaxy, this is towards the galactic center, and we're in the disk of the galaxy looking out. And in that galaxy lives the stars that I know and love, which are called pulsars. So this is a mock-up of our galaxy, and I can move it around so you can see that if you look at edge-on, which is kind of how we see our own galaxy, there's this central bulge, as well as these spiral arms. And the spiral arms are the site of star formation. So stars are big chemical factories, and if we could cut away a bit of star and look inside, which we can do with theory, even if we can't do it with experiment, we'd see that they're the sites of nuclear fusion. So protons in the center of stars are heated up so much that they can fuse together, and you end up with a process which, although it might be slightly more complicated than this, ends up producing helium in a nuclear reaction. And so when I was growing up, there were these bumper stickers you could buy which said solar, not nuclear, but in fact solar is nuclear energy. And stars are big chemical factories, and they've caused the hydrogen to be converted into helium. And when all the hydrogen runs out, the core of the star actually collapses, and it gives off a lot of gravitational energy, and it drives the temperature up to the point where helium atoms can then combine to form other elements in the periodic table. And so if you like, we're putting in atoms into the system, and when hydrogen is being fused to helium, it gives off a certain amount of energy. But when you turn helium into carbon, it has even more impact. And the centers of these stars get extremely hot, and the time between fusing hydrogen to helium is a lot longer than it takes for helium to carbon and so on. And so the outer layers of the star, when the chemical elements collapse, peel off, and in our system the sun will swell up and it will actually envelop the Earth. The good news is this isn't going to happen for about another 5 billion years, so we've got a bit of time to work out our escape plan. But the outer layers of the star will eventually peel off. The sun's a little bit boring in terms of its size, and so when the outer layers peel off, we'll create something called a planetary nebulae, which is a very beautiful object that occurs naturally in space, and here's some of them. And if you look carefully at the core of all these planetary nebulae, there's a little white star here. That's called a white dwarf. And the white dwarf is only about the size of the Earth, and you can think of it as the ashes of the star. So we'll have a look at a few of these as they whiz by. Some of them have these bizarre shapes, something to do with the rotation and magnetic field of the star and the local environment. So that's the fate of our sun. Fortunately, it's not the fate of every star. Larger stars have a more explosive ending. And so we're going to meet a star, which I think is called MB8782, which happens to stand for Matthew Bales in my phone number. So you've got to be careful. If you want to ring me at Swinburne, you know my extension. So the sun is what's called a G2 star. It lives for about 10 billion years, and it's currently about halfway through its life. MB8782 is only going to live for 12 billion years. So if you make a star 10 times heavier, it only lives for about 1.1% of the time, because it just burns all its fuel quite bigger. You might think that if you make a bigger star, if you added more fuel, a star would live for longer. But it doesn't. It heats up so much, it burns the material much more quickly. So MB8782 here is only going to live for about 12 million years before it becomes an enormous chemical factory in its core. And it'll burn all the hydrogen into helium and then so on, and it gets to silicon. And in about a day, it burns all of its silicon to iron. And then the center of the star can no longer keep itself supported against gravity, and all of the protons and electrons in the core are forced together, and they form a neutron, and that causes the center of the star to collapse. It only takes about 1/10 of a second, and that blows off the outer layers of the star, and you end up with something called a supernova remnant, which we see an animator's impression of here. We can actually look at real ones. Here is a bona fide supernova remnant. In 1987, when I was doing my PhD, this star did the good fortunate thing of blowing up for me in the Large Magellanic Cloud. And this is what it looked like some 20 years later. The material was expanding into the local galactic environment, and it lit up this beautiful little tree, and that's the center of the supernova remnant right there. If we want to look at other supernova remnants, this is one of my favorites. This is the Crab supernova remnant. In 1054 AD, a very large star blew up about, I think it's about 5,000 light years away. And this gave off so much light that in the evenings, it used to cast a shadow. It would be a cool thing to be able to witness. The supernova in the Magellanic Clouds was about 50 times further away, so it was about 2,500 times fainter than what this was. So this was so bright you could see it during the day, and at night it would cast a shadow. And right in the center of this supernova remnant, there's actually a neutron star. And this is an animator's impression of a neutron star. I might just stop this. So here it is. This is about 20 kilometers across this time. It's composed almost entirely of neutrons. There's a few superconducting protons and electrons in it. It has an outer crust and a superfluid core and a very large magnetic field represented by these green lines. It also has this beam of radio emission that comes out. And if you're very, very lucky, this beam will strike your telescope, and then you've got a chance of seeing it. If you're looking at it from the wrong angle, if I was looking at it from here, I wouldn't be able to see anything. But if I get correctly oriented, I get a beam of radiation once per rotation period. As we get further and further from the neutron star, the beam gets fainter and fainter. And by the time we get to planet Earth and try and look for one of these things, the amount of energy coming to us is so small that all of the neutron stars shining at the Earth, all the information that's ever been collected is less than the energy of a raindrop. So fortunately, you can carry a lot of information in radio waves. And my team here, is actually observing a neutron star as we speak. So I'm going to plug in my other laptop and hope it's not a catastrophe. So we're crossing live now to the Milky Radio Telescope. I hope. Let me just... Here we go. It's working. Incredible. Okay, so we're actually observing a neutron star right at the moment. And this is our view of the night sky. That's overhead over Australia at the moment. And these are all the neutron stars that we can see in the sky. So each of these grey dots represents a neutron star. I'm going to attempt something very brave and try and make this go full screen. Don't try this at home. Oh, my neck. Doesn't seem to want to do it. All right, we're going to click on a neutron star. That was brave. So this is actually a computer about 600 kilometers from here that I'm operating from this lecture theatre, courtesy of Melbourne University's internet. And a lot of what I'm seeing is just the noise present in the telescope. So this is the Milky Way Radio Telescope. It's a mile long and 11 meters wide. And it's collecting data from the neutron star. And this is actually the pulse of the radio emission from this star 1141 minus 6545 as it was observed just a few seconds ago. So the neutron star's beam went sweeping past the radio telescope, and this is what we saw here. And you can see there's a lot of noise, but then there's the pulse, which is very nice. And then if I could control that, this is what we call a waterfall plot, because it looks a bit like water. And this is the neutron star's pulse as a function of minutes. So this is 7 minutes of data here. And you can see the pulse drifting through here. This is because I'm not predicting precisely when the pulse should be arriving. I've got it a little bit wrong. We'll have a word to the students in the audience a bit later about that. But basically, I can use when those pulses hit my telescope to map out the orbit of this system. So we might go back to real presentation. Speak to me. There we go. Curly wheel, it's never good. Glad to hear it. Right, that's better. Just can't rush it. Okay, sorry about that. So pulsars were first discovered in 1967 by Jocelyn Bell. There's now over 2,000 of them known, and about 130 of them are in these dense regions of, or these clusters that orbit our own, called globular clusters, and they rotate incredibly quickly. So even the slowest one rotates once every 8 seconds. So you've got something 20 kilometers across, and it does a complete rotation in 8 seconds. And in fact, one of our students recently discovered one rotating every 12 seconds, so I need to update this slide. But the fastest is an incredible 1.4 milliseconds. So you've got something 20 kilometers across, it's whizzing around about 700 times a second. And it may seem impossible that can actually be true, but I've discovered them, so I kind of believe it. If you look up at the sky, this is a map in galactic coordinates. So this is the North Galactic Pole and South Galactic Pole. Our galactic plane lies along here, and most of the pulsars live near the galactic plane, but there's just a few ones that are more local, and they appear off the galactic plane. They tend to be very close to us. If we look down on the galaxy, the sun is here, and all of the known pulsars, as opposed to every pulsar that exists, these are the ones that have been discovered by astronomers in surveys. And the galactic center is about here. And ones over here are just too faint, or they're traveling through too much rubbish for us to see them. So this is where the sun is, and these are our pulsars. And each red circle is a neutron star. And there's a couple of equations. This is a little bit scary. This is called calculus. The amount of energy per time that is given off depends on the magnetic field strength of the neutron star squared divided by how fast it's rotating to the 4th power. So if you've got a nice big magnetic field, you give off a lot of energy. And if you've got a small period, you give off even more energy. So when we're trying to understand our neutron stars, we can work out their magnetic field by working out how rapidly the pulsar is spinning and how rapidly it's slowing down. And when we're trying to work out how old it is, we can do that by looking at how fast it takes to rotate and how fast it's slowing down. So basically the age depends on how fast you're rotating and how fast you're slowing down, and the magnetic field is how fast you're rotating and how fast you're slowing down as well, but in a different ratio. And so we can plot this diagram, which is called the magnetic field period diagram, and you can plot where various neutron stars live on this. So this is how magnetic you are, and each one of these big tick marks is a factor of 10. And then this is how fast you're rotating, and again this is a factor of 10. So these are these super fast pulsars going 700 times a second, and this pulsar out here is the 8-second pulsar. And I have to redo my diagram because there's now one at 12 seconds. So that Crab Nebula that I showed you before, the star that exploded in 1054, its pulsar is over here. It's very young. It rotates every 33 milliseconds, so about 30 times a second it rotates, has a nice high magnetic field, and it's giving off a huge amount of energy. And so what the neutron stars do is they're born over here, and then they quickly slow down and join what we call the island, the pulsar island. You can get booted off it in a sense. If you lose too much energy, you stop shining and you die, and you enter what we call the graveyard over here. So your average pulsar is kind of born fast and young, and then it spins down quickly. After it's about 1 million years old, it's just part of one of these boring pulsars, and then they die. But then you've got this tantalizing trail down here for these other objects, and you might wonder, well, how do they get here? There's this little trail that sort of gives it away a little bit, and it is actually possible to go from the island down here, but in order to do this, you need a special set of circumstances to occur. You actually need a star that is living next to you and is swelling up. So you remember earlier on I said that at the end of a star's life it swells up and becomes a red giant. Well, if you're a neutron star at the center of this disk here, you can get a circumstance where, here we go. If you're a nice big star living next to a neutron star, so I'm going to be a big star here, what can happen is that as I start swelling up, the material on the edge of me looks at that neutron star, and the gravity on it is so powerful it thinks, you know what, I'd rather fall on to him than stay attached to you. And so I haven't drawn in the star here, but basically it rips material off the outer edges, and they go into this orbit around the neutron star, and it hits the neutron star, and that gives off energy, and so the material moves in a little bit, and the inner parts of this neutron star are rotating, or this disk, it's called an accretion disk, are rotating more quickly than the outer layers, so they rub. And that rubbing gives off energy. And in fact, this gives off so much energy that it turns the gravitational energy into X-rays. And if you grab an X-ray telescope and stick it above our atmosphere and look out at the night sky, there's about 100 of these things that you can see in our galaxy at any one time that are ripping material off and turning it into energy. Now, it turns out that the amount of energy that they give off is so much that on the surface of the neutron star, the energy output is equivalent to 100,000 nuclear wars going off every second. And yet it doesn't destroy the neutron star, because the neutron star is so incredibly compact and heavy. So let's just see how that works. The colors here represent temperature. So blue is cool and white is hot. And the material spirals in. And if you're in the middle, because it's rotating so quickly, it actually makes the neutron star spin faster and faster. And so this is how a neutron star can get from the island to those very rapidly spinning pulsars we call the millisecond pulsars, because the material, as it's about to strike the neutron star, is going at about 30% of the speed of light, or about 200,000 kilometers every second. And that makes the neutron star spin faster and faster and faster, and it helps keep the neutron star alive. And so this is some real data from this romantic pulsar here, 1600 minus 3053. It was discovered by one of my students. And this is a pulsar that only has a pulse period of 3 milliseconds. So the neutron star is off, and then the beam hits us, and it's got this funny shape, this nice little spike. And pulsar astronomers love neutron stars with spikes because it means we can work out when the pulse hits our telescope very accurately. And what we do is we work out when that neutron star strikes the Earth. We know the Earth's going around the Sun, and we can use this as a measurement tool to map any orbit that these neutron stars might be in. And in fact, this is kind of what I do for a living. I build supercomputers that go on the back of these big telescopes, and this is another neutron star. This one rotates every 8 milliseconds, and you can see its little pulse here. And what we do is we work out when that pulse would have hit the Earth, and we try and do all sorts of experiments with it. This is my favorite pulsar, 1909 minus 3744, discovered by Brian Jacobi, who was one of my students over 10 years ago. And the pulse on this neutron star is so narrow that it's only 40 microseconds wide. So in 40 microseconds, this pulse comes and goes. And you can measure when it hit the Earth to amazing precision. In fact, you can usually measure it to about 100 nanoseconds, which is 0.701 seconds. And so if we look at this neutron star over the course of many years, this is when we discovered it, we can actually measure it. And if we take off all of the effects of the Earth and the effects of the orbit, we get what we call our residuals, and it's 154 nanoseconds is the average error we get in determining when this pulse hits our Earth. And we can actually use that to do some very cool things. So if we plot those, what we call arrival times, as a function of the orbital phase of the pulsar. So the pulsar is actually going around another star, and it takes about a day and a half to go around. So this is a day and a half from 0 to 1 here. And as it goes past the pulsar, it gets induced in it a time delay because it's going around the orbit. If we subtract that time delay because the orbit is almost perfectly circular, this is what's left behind. And this is actually a relativistic time delay. So as the neutron star goes behind its companion, space-time shrinks near the companion according to Einstein's theory of relativity, and the pulse takes longer to reach us than it would if the star wasn't there. And you end up with this nice cuspy looking thing, and this delay of 12 microseconds, or actually it's about 15 from here to here, is exactly what Einstein predicted it should be if the companion had a white dwarf mass of around about 0.2 solar masses. So we can actually use Einstein's theory to measure some incredible things. So the rotation period of this pulsar is 0.0029471080681076401 plus or minus 9 in the last place seconds. And I'm actually being a bit lazy. I made this slide about 7 years ago. I think it's now another few decimal places. And the mass of the pulsar is 1.44 times the mass of our Sun. And this is one of the most accurately known masses in the universe. The other amazing thing is that the orbit of the neutron star as it goes around its companion is about 1 million kilometers in diameter, and it's an elliptical orbit, which means it's not a perfect circle. And we can measure the difference between the semi-major axis and the semi-minor axis. So all orbits in astronomy are elliptical, and this one here has a difference between these two distances of just 5 microns. So it's a perfect circle. It's 1 million kilometers long, but it is oblate by 5 microns. And we can actually measure that very accurately, which is incredible. So these things are really naturally occurring gravitational laboratories. Here's another one we discovered about 1993. This is actually the white dwarf companion to the pulsar. You can't see the pulsar, and you might wonder why it's black. It's because this is a negative image. But one of my students for his PhD measured the proper motion, or the direction this thing was traveling, and got the arrow. And John Bell, who was my first PhD student in Australia, discovered this bow shock. So what's happening is the neutron star is giving off a lot of energy. That energy impacts electrons that are in our galaxy. The light hits them, and it causes this bow shock, as if this is a ship going through the ocean. But instead, it's a neutron star traveling with its companion. And we actually know the distance to this neutron star to an accuracy of 0.1%. It's 156 parsecs away. This is the brightest pulsar in the sky, and fortunately it's 47 degrees south of the equator, so none of our competitors can see it. It's a 5.7 millisecond pulsar in a 5.7 day orbit, and was discovered in 1992, shortly after, or just before I came back from the UK. And I actually did my postdoctoral research on a survey to discover this system. It gives off X-rays, ultraviolet and radio emission, and this won't mean a lot to you, but to a radio astronomer this is heavenly, because it's about 100 times brighter than the next brightest pulsar. Because of that, we can do some cute things. Einstein predicted that the orbit should be perturbed because of the curvature of space-time in the following way, and we wrote a paper in Nature back in 2001, which showed that Einstein's prediction agreed with our data beautifully. The prediction is this quasi-sinusoidal pattern, and this is our experimental data. And we actually measured the accuracy of these points was 34 nanoseconds. So we could measure when the pulse was coming to an accuracy of 34 nanoseconds in order to confirm Einstein's theory. And this is what the profile of the pulsar looks like. It's got this amazingly complicated shape, and it's even got these little kind of notches here. And I actually named these, it's a bit like a mountain. I named it after the student of mine who discovered them. It's called the Navarro notches. And I don't know what's causing them, but they're always there. One of the other interesting pulsars that was discovered by Ben Stappers, another one of my students, is this pulsar here. It actually rotates every 4.5 milliseconds, so the animator hasn't quite got it right. But we wanted to slow it down so you could see it. And incredibly, every 3 hours, it has a little star that orbits it. And the neutron star gives off gamma rays, which light up one side of the star. And the gamma rays are reprocessed into optical light. And so John, for his PhD, took these images, I like to think of them as iconic images, and it takes about 15 minutes on the world's largest telescopes to actually see this companion star. But we found that there was a star which was coming and going just there in phase with the orbit of the pulsar. And that's actually what you're seeing just near my blue light is the reflected light from the neutron star on this companion. And that enabled us to determine whether the system was edge-on like this, or if it had been face-on, the amount of light we were getting from the star would have been roughly constant with time. And the optical images showed us that wasn't the case. So we managed to measure the orientation of this system so we could do our physics experiments with it more precisely. There is another remarkable pulsar called the double pulsar, and it's the best laboratory for testing Einstein's theory of relativity. And unfortunately, I had nothing to do with the discovery of this one. But one of my friends, Marta Berge, discovered this and was actually awarded a prize on Melbourne Uni campus for it. So this pulsar here was discovered in 2003. We've done a much better job at beautifying the beam this time. And And in the discovery plot, it was very apparent that it was highly accelerated. So normally when we try and discover these pulsars, we look for the pulse. This one has this very unusual shape. It has a sort of what you might call the leading pulse, which has these little nice features, and then this secondary pulse. And it takes 22 milliseconds, or 22.7 milliseconds for this pulsar to rotate around once, and it's got its beam that's shining out into the universe. And fortunately, this one points at the Parkes radio telescope and was discovered there by Marta. And she soon realized that it was orbiting something. So here's its pulse again. So by timing when this pulse hit the Parkes telescope, she actually quickly learnt what kind of shape the orbit was in. And it was obvious that it was going around another star, but she didn't know what that star was. But luckily, Einstein showed us that because this star is traveling around at about 300 kilometers per second, the shape of this orbit actually does what we call a precession. And you get these beautiful rosette patterns happening because the speed of gravity is finite. If the speed of light was infinite, the elliptical path that this traveled along would not change. But because it's actually being accelerated to where the other star used to be, not where it actually is, Einstein shows us that you can use this formula to work out how rapidly this rosette pattern should advance. And in this system here, it's 16.7 degrees every year. So not quite as fast as it is in the animation. When general relativity was first invented by Einstein, the most relativistic system we knew of was Mercury going around the Sun, and it was 43 arc seconds a century. So 43 3600ths of a degree every 100 years, and this system here is 16.7 degrees a year. So it's an amazing gravitational laboratory. And so Marta was able to use the fact that she knew how rapidly the elliptical path was precessing to constrain the mass of the pulsar and whatever its companion was to lie somewhere along this dashed line. So this is what's called a mass-mass diagram, and the aim is to try and measure the masses of the stars. So she did that, and so we knew that the sum of the two masses, I think it's around 2.5 or 2.6 times the mass of the Sun. Another one of my former students, a guy called Duncan Lorimer, was at the Parkes telescope a few years later, and he had written a special piece of software to find accelerated pulsars. And he thought, what can I test it on? And so he looked at the double pulsar, which was the most relativistic system we knew about, and read it into his software, and you could set the orbital parameters and check whether your software was working right. And he then changed the sign of the acceleration, or got it wrong or something, and he found that there was another pulsar going around the first pulsar. So this became the first neutron star system where there was another neutron star that was also pulsing. And so by measuring the shape of the two orbits, you could actually determine another constraint, the mass ratio. And when he did that, he could work out, or he and his colleagues could work out the pulsar was 1.3 masses and the companion 1.25. Now fortunately, Einstein tells us that if ever you get two stars going around each other, they should give off gravitational waves. And this orbit should shrink by 7 millimeters a day if the two neutron stars obey general relativity. So pulsar astronomers were armed with this incredible knowledge, and all we had to do was see something about 10,000 light years away shrink by 7 millimeters, and we were in business. Unfortunately, because the orbit shrinks, the two stars get faster, and they get closer, or they get faster and faster with each orbit, and this actually builds up with time. And they proved that the this gives rise to what we call an orbital period derivative, and that gave rise to this other constraint here. So on this mass-mass diagram, everything had to intersect, and they could show it intersected at this very tiny point, and it proved that gravitational waves existed. This repeated an earlier experiment by Joe Taylor and Russell Holtz, and they were awarded the 1993 Nobel Prize for doing a very similar experiment, but using a slightly different metric to determine the masses. So I saw a talk the other day on this system, and this experimental error is now down to, I think it's 0.01%. So Einstein's right at the kind of 99.99% level. And because this orbit shrinks 7 millimeters per day, in about 80 million years, these two neutron stars will be going around each other 1,000 times a second. I've slowed it down here for you. And they'll get so near each other that the two neutron stars will go into this amazingly tight orbit. So we've got these two neutron stars, they're 10 kilometers across, they weigh 500,000 Earth masses, and they're going around each other 1,000 times a second, and they're giving off an amazing amount of gravitational waves. In fact, they're giving off so many gravitational waves that they tear each other apart in an enormous explosion, and they give off a solar mass times c² of energy in about a millisecond. And that travels through the universe, and when it interacts with something like the LIGO interferometer, it causes the mirrors to shake, and they measure it. And so the whole LIGO instrument was actually designed to detect coalescing neutron stars. Because we knew that neutron stars existed, black holes were not as well known. So we know that there's 8 binary pulsars in our galaxy. We know how many galaxies there are in the universe and how far away they are. And we know how sensitive the LIGO interferometer is. So we can combine how many galaxies there are, how many pulsars there are in our own galaxy. And the prediction, unfortunately, is rather uncertain. It predicts that between a few and what I'd call tons of neutron stars should merge in the advanced LIGO horizon every year. But unfortunately, it's very hard to observe black hole binaries because they don't give off any light. So these were kind of like theoretical conjectures. And it's amazing that we built an instrument in order to detect these neutron star mergers, but we ended up detecting these black holes merging. So I think that was an amazing achievement. And pulsar astronomers are yet to be beaten. So we've actually got these millisecond pulsars at numerous places in our own galaxy. And if you get big enough black holes, they actually change the space between you and the millisecond pulsars and cause those pulses that I showed you to be delayed. And so a whole group of us around the world are part of what's called the International Pulsar Timing Array, and we're trying to detect gravitational waves from supermassive black holes. And I've got how long have I got, David?
Oh, another 10 minutes.
Excellent.
No one's leaving yet.
Right. So what I'm going to show you is a bunch of both real data and 3D supercomputer simulations of our universe. And we're going to start with one of these accreting neutron stars. So earlier on I showed you what was the experimental data, but here is we've taken that into an animation package. And this shows you how one of these millisecond pulsars ends up traveling as fast as it can. It has a star near it, which swells up at the end of its life. The material on the edge falls onto this, tries to fall onto the neutron star. It hits material that did that a few years or thousands of years before and forms this accretion disk. And this accretion disk provides a torque on the neutron star which spins it up to these amazingly high speeds. And what you're seeing is a supercomputer simulation of how that works. And the colors here represent the different temperatures. So blue is hot and red is cool. And these accretion disks get so hot they can actually fuse helium. If we do a survey of the universe to work out where the galaxies are, this is what we see. Each galaxy here is at a real position from one of our surveys. Unfortunately, because of the Milky Way, it kind of gets in the way and we can't see the galaxies. But this is where what's called the 3DF Galaxy Redshift Survey saw that galaxies existed in our universe. If we look back into the cosmic microwave background, so this is what the universe looked like 300,000 years after the Big Bang, and it wasn't quite smooth. And the difference between the hot bits and the cold bits is only about 1 part in 100,000. But that's enough to make the universe be what we call non-isotropic. And if you turn on gravity and watch what happens if you have those initial conditions, you can see that you get this beautiful filamentary structure starting to form. And so this is actually a supercomputer simulation. It took us about a month to run it. But it shows you how material in the universe clumps together. And at the junctions of all these filaments and along them, we get actually galaxies being formed. And so what you're witnessing here is like 13 billion years of cosmic evolution. And we're going to fly in a minute and see an individual galaxy form. Just before we do that, though, this is the 2DF Galaxy Redshift Survey. And if I freeze this at the appropriate angle, you can see that these slices of the universe have more galaxies than other. So this is the galactic density in these two wedge-shaped regions that my colleagues up at the Siding Spring Observatory did. And then this is a supercomputer simulation. And you can see that the kind of structures we're predicting from the simulation largely agree with what we see in reality. So if we go back to our cosmic simulation, if we zoom into one of these regions that are collapsing under gravity, we've sort of taken out the large-scale expansion of the universe just so you can see it a little bit more easily. At the cores of these high-density regions, you actually get galaxies being formed. And so we took our supercomputer and then just cut a box out of this simulation and did it in higher resolution. And what you're going to see in a minute is an actual galaxy being born. So it looks like we're heading into this guy. So the collapse on all scales looks kind of similar. And so this is a many million particle simulation of a little local part of the galactic web. But this time we've turned on our ability to sort of create stars. And so over the course of billions of years, the material clumps together and you end up forming a galaxy like the pictures I showed you earlier in the talk. And this is how our Milky Way formed. The parameters we've put into this system are such that you end up with a Milky Way-like galaxy. So you can see at first it's quite chaotic and there's all these streamers and everything happening. But over time it relaxes and you end up with a disk of stars, about 100 billion of them. And we were fortunate enough to be around a star that had a planet suitable for life. And we can now learn about how these things are created. So that's the kind of core of the galaxy, and you can see the spiral arms. This is another simulation, but this time we've frozen time. We're just going to fly past it to give you an idea of the shape. This was done by a guy called Jeremy Balin for me. And you can see the simulations are reproducing the shape of these galaxies very nicely. Now, at the cores of these galaxies, there's actually a black hole. And it's a black hole that is much larger than our sun. They're actually up to 1 billion times the mass of the sun. And if ever you get two galaxies going near each other, they actually coalesce and sort of devour each other. And you can imagine the two black holes here sink towards the middle of this coalescence, and they actually enter a binary system where you've got these two very large black holes going around each other, and those black holes give off gravitational waves, and they travel throughout the universe, and they travel between us and our pulsars. And so one of the things our group is trying to do is to detect the presence of these supermassive black hole binaries in the universe by looking at the neutron stars. To look at the galaxy simulation in a slightly different way, I'm being God here, and I've created a small section of the universe. It's not quite smooth, and we need it to be not quite smooth, otherwise it would just stay a very boring shape. It's got the same density variations as the cosmic microwave background. That's the universe as it looked 300,000 years after the Big Bang had. And what I'm going to do is I'm going to start time, and you're going to see the material clumped together. And at the cores of all these little kind of proto-galaxies are these black holes. And when the galaxies merge, you end up creating a galaxy. And you can imagine if there's a little black hole in all of these things, when they meet, they coagulate into bigger ones, and that gives off this background of gravitational waves. Unfortunately, it's at very low frequencies. So it's only about they go around each other about every 10 to the 9 seconds, or something like every 30 years ago, or 30 years or so. So we need to observe our neutron stars for a very long time. And the ultimate way to detect this is to build a bigger and better telescope. And this is an artist's impression of the square kilometre array. This part of it's being built in South Africa. These are 13.7 metre dishes. And the ultimate aim is to build 3,000 of them. That's proving rather costly, so I'm not sure we're going to get that many. There's currently 16, but there's enough money to build another 168, I think. So in phase one, we're going to build 192 dishes. And these things are going to look at the pulsars and try and measure their arrival times so accurately that we'll detect these gravitational waves as the supermassive black holes perturb our pulsars. The other thing that, just getting back to the gravitational wave event that LIGO's already seen, the question is, where did it come from? Was it just two stars in the outer reaches of the galaxy that were going around each other and always going around each other? Or did they come from these globular clusters, which are these dense clusters of stars? And so we can do a simulation of a globular cluster. If my program hangs together. Please, yes. Right, so I'll just spin that so you get a bit of a better 3D likeness of it. So globular clusters have all of these stars, and the heavy ones sink to the bottom. And the idea is that if you have a black hole, it'll sink to the bottom of this cluster and have a chance to interact with other black holes. And so some people think that the two black holes we saw coalesce last year were just from two big stars that lived in our galaxy and didn't interact with anything. And other people think that they came from these globular clusters. So I'm going to turn on time. I can remember how to do it. And we're going to see how these stars all interact with each other. And if you're really, really clever, see if I can zoom out a bit. You'll see that every now and then one of the stars gets kicked out. So let's just turn that on. So there they go. And you can see these stars get flung out. And every now and then they have these what's called a three-body encounter. And they throw stars out. When they do that, the rest of the stars get what we call heated up. And the core collapses, and you can form these very exotic binary systems with black holes, and one just flashed out there. And so some people think that the black hole binary that we saw was created in some sort of encounter like this, and other people think that they were produced in just the outer reaches of a normal galaxy. I think this would be more exotic, but it may not be true. So that's one of the questions we want to try and explore as we detect gravity waves in the future. So in conclusion, pulsars gave astronomers confidence that general relativity was correct, and they also gave us a guaranteed source of events that would eventually coalesce out in the universe. Astronomers constructed LIGO, this gravity wave detector, and it saw them, which is, I think, is one of the most amazing things one of the amazing graphs I've ever seen. In the future, the square kilometre array, which is that big array of dishes, will give us the opportunity to see black holes from, or gravitational waves from supermassive black holes, and also to study our pulsars even more accurately. So I might conclude there and hand back to David.
Given that we've gone all around the universe and back again, that's taken a little bit of time, so I might just take two pressing questions given the lateness of the hour. If there's someone who'd like... Yes, the gentleman right in the middle. And I'll take you next.
The radio telescope array in South Africa, I was intrigued by the fact that it's not set out in a regular grid, but looks to be deliberately random. Is that for some reason, for resolution purposes, or just...
So the question is, why are the telescopes kind of clustered in the middle and then quasi-randomly spaced? The idea is you don't want any two telescopes to have the same separation, because we actually combine the signals from the two telescopes a little bit like your eyes do, and if we have different spacings, we get information about different spatial scales on the universe. So if you have them very close, you learn about the big structure. If you put them far away, you learn about the fine structure. And so there's an optimal spacing. You have more in the core and then progressively less and less. And you try and make sure that no two telescopes are the same distance apart, because that doesn't give you new information.
Okay,
Good
so
question.
One quick question from down the front here.
The discovery of gravity waves was kind of...
That's the microphone.
Oh, sorry. I was just...
I'm not going to kiss you.
No, that's all right. You're welcome to. Anyways, there's... so you think gravity waves are kind of the biggest... There was a quote, it was the biggest kind of discovery of a generation. What's the next thing? What's the next kind of big theory that can be confirmed through observation or something like that?
So at the moment, we haven't linked gravity to electromagnetism or the other forces. So there's four fundamental forces in nature. Gravity seems to sit outside of them, just doing its own thing. And we can't reconcile quantum mechanics and gravity. And so I think the next big thing is to combine what's called the grand unified theory of everything, basically. So we want to combine gravity and electromagnetism and the strong force and the weak force into one. Another good thing to do would be to understand what the dark matter comprises. So there's a lot of the universe that we're unaware. We know it's not atoms, it's not electrons and protons, so we don't know what the dark matter is, and that's a large fraction of what we call matter in the universe, or missing matter. And then there's this other thing, dark energy, which Professor Brian Schmidt was involved in discovering. That's even more mysterious. One of my colleagues said you can only invoke the tooth fairy once. So we have this unfortunate thing that we have dark matter and dark energy that we don't understand, but we'd also like to combine all the forces together.
Okay, well that's an excellent note to end on, because certainly when we've accomplished all those things, you'll hear about it in the future July lecture. So in the near term, there are two further in the program. Next week, Friday night, please note, it's scheduled to be in the Lyle Theatre with an overflow in the Revette directly above, just in the building next door. Unfortunately, we couldn't get this theatre. But the final one on July 29 will be back in here, and I invite you to come back on those two Fridays to hear the next story in Einstein's magnificent theory. Ladies and gentlemen, thank you again for coming. Safe travel home.